turn that on. All right. So we've already started talking about concepts in probability, and we're going to continue the conceptual basis of the foundation that you got on Tuesday. And we're going to build on that now and talk about this thing that we call conditional probability. And what we're going to do now is we know how to display our probability using a table. All right. But now we're going to talk about what we call a conditional probability. And conditional probabilities work like this. A conditional probability is just the probability of an event A given information about the occurrence of another event B. All right. Give you an example. Hey, do I have your can I turn your cameras on real quick, please? Turn your cameras on for me, please, if you can. You're in a position to do so. And y'all can't see. I don't know if y'all can see what I can see. I don't think y'all can see each other. Can y'all see each other? How do I make it to where y'all can see each other?
Yeah, I can see everyone.
Oh,
I can see a couple of them.
Okay, so look, here's what I want you to do. I want to know the probability that you are I want to know the probability that you wear glasses. The probability that you wear glasses, given that you're a male. Everybody got that? The probability that you wear glasses, given you're a male. Everybody understand that? That's what I want to know. So if I were to ask you this question, this is basically a two-part question. And the first part is this. In my particular sample, right now, if I look at everybody's camera is turned on. Everybody got that? And if I look at that, I can break that down into either males and females. Now, am I interested in every particular person's camera being on right now? If I say the probability you wear glasses, given, what was it I said? I feel like I said it was given that you're a male, right? Yeah. Probability you wear glasses, given that you're a male. Everybody got that? So I need to see how I can see your faces. Speaker. I don't want to be speaker.
I think you gotta stop sharing so you can see everyone.
Yeah, I can't see everyone, but y'all can see each other. Oh, there you go. There I go. There we go. So right now, I have people with their cameras on. Am I interested in everybody? No, I'm only interested in who right now first. In order to actually be in the sample, can you be a female? Yes or no?
No.
I'm only interested in who then?
The males.
The males to begin with. So what ends up happening when we talk about a conditional probability is we restrict our actual sample. We start off with a big sample. So everybody turn your cameras back on one more time for me, please. Cameras back on if you can. People that can, I guess y'all can't turn them on. Thank y'all. Thank y'all. So when I look at all these beautiful faces in this class right now, I'm gonna ask some people to shut theirs off. And here's what I'm interested in. I want to know the probability that you wear glasses given you're a male. So the first thing I need to know is who are my males in the classroom. So if you're a male, leave your camera on. Everybody else shut your cameras off. Thank you so much. So I should only be looking at males right now. Thank y'all so much. Good. Now, out of my males, who am I interested in now?
The ones with glasses.
So if you have glasses on, leave them on. Leave your cameras on. Everybody shut your cameras off, please. Everybody else shut those off. So right now, I can see only males with glasses on in my sample. Everybody got that? All right, thank you for participating. You can turn your cameras off or on if you want to. Appreciate that. So what we're gonna do now is this, and we're gonna talk about this conditional probability. And we call conditional probability is written as the probability of A given B. The probability of A given B. And mathematically, we use this symbol right here, the vertical bar. This says A given B, and here's what this means. Given that B has occurred, in this case, if I say the probability that you wear glasses, given that you are a male. Let me write those out so we know what those are. The probability that you wear glasses, given that you're a male. Again, who am I interested in? Am I interested in everybody in the sample? No, I'm only interested in the male. So the first part of the sample is the restriction I'm going to place on it. And every time I do a conditional, I always place my restrictions first. So I know I'm restricting it to the probability that you are a male. I have to restrict the denominator of the fraction, the probability that you're a male. And then once I got it restricted to a male, the next thing I'm interested in is, are you a male and do you wear glasses? Remember the word and is the intersection. So we're actually interested in the probability of glasses and being a male. And this is how we develop the formula. We always start by restricting first, and then we look at the intersection between the two events. And that's what we're going to work on tonight. We're going to start with a restriction, and then we're going to look at the intersection between that restriction, all right? So the way we show this, we can use one of two methods. One method we already know is what we call our two-way tables, or our contingency tables. An easier method for me, it might be for you too. Some of you may just prefer two-way tables. An easier method for me is what we call a decision tree. And so here's the problem we were talking about on Tuesday about electronic rub and the TV with the faster rate and the standard rate. And if it had a streaming media player or if it didn't have a streaming media player, right? So our two events were, first event is going to be your refresh rate right here. It's one of the events. And it can be faster or it can be standard. Second event is going to be your streaming rate. And it can be yes or no. Either it has a streaming media player, either it can be yes or no. So when we make this tree, here's what I want to know. Here's the problem. It says that Electronics World, a survey was sent to 300 customers who purchased large TVs, asking if the television, whatever. What is the problem that I want to do with this? Oh, here it goes. So all I want to do is I want to take this table right here, and put it on this tree. And so if you look at this table, it starts off by either you purchased a faster refresh rate TV or you did not purchase a faster refresh rate TV. And remember, that means that if we give these letters, I'm going to give them letters. We call this one right here F, and the standard is F prime. So here what you have is F and F prime, which means the standard rate is not a faster refresh rate TV. In this particular sample, how many people purchase a faster refresh rate TV? Can you tell me that? How many people purchase a faster refresh rate TV?
80.
38.
So let's look at it.
80.
Faster would be who? All of these people right here. And how many people is that?
80.
80.
Oh,
So
okay.
all these people have purchased
80.
a faster refresh rate TV. So we'll put in here 80 out of how many people?
300.
Out of
80
300.
out of 300. How many purchase a standard rate TV?
220.
220
out of
220.
out
300,
of
right?
the 300.
Now, if I add my numerators, 80 and 220, what should I get there? I should get 300.
300.
Everybody got that?
300.
That's all the people who purchase a TV. Now, next question says this, and if you read along the branches, the branch says, these people purchased a faster refresh rate TV and what else did they do? Purchased a,
Streaming media player.
that means that their faster refresh TV came with a streaming media player. How many people is that?
38.
38.
38. That's these people right here. And that's 38 out of how many?
108.
No, it's 38 out of
80.
how many people
300.
purchased the TV still? 300.
Oh,
We're looking at the
300.
sample.
300.
Yes, don't change that. How many people did not purchase a streaming media player then?
42.
Out of how many?
300.
300. How many people did not purchase a faster refresh rate? So they purchased a standard TV, but it came with a streaming media player. How many is that?
70.
These 70 people. Out of how many total?
300.
300. How many did not purchase? How many did not purchase the faster refresh? And if you not come with
150.
the streaming media player, that would be 150.
150 over 300.
Good. So this is me taking this table right here and putting it into a tree, into a decision tree, all right? I like decision trees myself. I like them more than I like tables, actually. But I want you to see how I broke it down. I took my two events, right? Faster refresh rate, standard refresh rate, F and F prime. And then I did a streaming media player next. And I didn't give those letters. Let me give those letters. Here is S. Here is S prime. So here is S. Here is S prime. Here is S. Here is S prime. Notice you have S and S prime on this branch, S and S prime on this branch. And that's because you can have a faster TV with a streaming media player, or you can have a faster TV with no streaming media player. You can have a standard TV with a streaming player, or a standard TV without a streaming player. And what I want you to realize is that you can actually reflip these branches. You could have did streaming media player first, right? So you could have made a different tree that went streaming media player first, where you had S and S prime and no streaming media player right here. Then you would have had streaming with a faster rate and streaming without a faster rate. You would have had no streaming with a faster rate and no streaming without a faster rate. But in the end, your tree would have been the same because of the way multiplication works. So just keep that in mind. You can make this tree a couple different ways, but you're going to get this end results. Because the goal now is when we set this tree up, we're going to multiply branches. All right, we're going to multiply branches. And so here's what I want to know now. Now that I have this tree set up, using the decision tree, I want to find the probability that a household purchased a streaming media player, given that the household purchased a television with a faster refresh rate. So given this tree here that we just completed, here's what I'm trying to find. And the key word I want you to see, and the key word I want you to look for, is going to be this word, given. That is the key word. Because given tells me, if I see the word given, given means you're going to restrict your denominator. We're going to restrict the denominator. So the denominator at the bottom is going to be restricted to something, which means I'm no longer looking at the entire 300 people. I no longer care about all 300 people. Just when I did male given glasses, right? Or glasses given male. When I said glasses given male, I restrict the denominator to just the males. So again, if I label this tree, here is F, F prime, here's S, S prime, S, S prime. All right. Hey, these notes are on Blackboard too, by the way. I know some of y'all don't realize that we have a Blackboard website, a Blackboard course for this, but there is one. Because I be getting questions all the time. I know I'll be answering them on Blackboard. That's okay though. That's why I don't check out emails on Blackboard. Hey, if you send me emails on Blackboard, I don't get them. So send them to my UHD account. Don't send them on Blackboard. They got lost for the last 7 weeks. I found somebody today that was on the first day of class. I was like, ooh, I ain't even reply. Delete. Hopefully somebody answered. Anyway, back to this. So now I'm interested in trying to find, they purchased a streaming media player given that the household purchased the television with a faster refresh rate. Question, how many of these branches have this streaming media player on it? Yeah, show me. Can we tell me where those at? How many branches do I have like that? Here, they have it too. Right there, right? They have it, and right.
And the purchase.
And this one right here.
Yeah, right there.
Both of those have purchased streaming media players. Everybody got that?
Yes.
But my question is, do I care about everybody that purchased streaming media player? I only care about who? The people that purchased it with a
faster.
But that's faster refresh.
So I only care about what people then? I only care about
38.
Not F.
I only care about this branch right here. And it's these 38 people that I care about, right? Everybody understand that? Those 38 people who I care about. Now, when I do this though, let's write the actual condition out. And it says this. It's the probability of a streaming media player. It's the probability of S given
F.
F.
Mm-hmm.
So the question becomes this back part is the restriction.
Okay.
That is my restriction. That's who that's who I care about. So in this sample, how many F's do I have in the sample?
80.
How many people purchased a TV? Purchased a faster refresh rate TV is a better question of saying that.
80,
Yes. How do we get 80?
because it's sitting there on top. It's 80 and the other
Yeah.
is
So this
38.
one, so you looking at the table. If you look at this table tells you it's how many people? 80. It's
80.
easy to see right there.
Mhm.
You can also see it from the tree though too, because you have how many right here?
38,
How
38.
many right here?
42.
42.
So that will be 80 people. So if I restricted it to just these 80 people, and these 80 people represent who? The
The people with the faster.
Refresh with the faster rate.
refresh rate. So those 80 people represent the faster refresh rate. Now, out of those 80 people, which ones am I actually interested in though?
38.
38.
Because those
The
people have
38.
what?
The streaming media player.
So they have faster refresh rate and streaming media, the streaming media player. Everybody got that?
Yes.
This is the quality of that bow. This meets the bow, or this is the intersection. By intersection, I mean it has both qualities. Look what you've done now. You've restricted your sample to how many people?
80.
How many did you start off with?
300.
And I've restricted it down to just these 80 people because these 80 people have the faster
Faster
refresh rate.
refresh
And
rate.
again, I know I'm looking at the faster refresh rate because it says, given that the household purchased what kind of TV?
Faster refresh rate.
When you do these probability problems, before you start doing any math, before you start doing any kind of math, I want you to look at the problem and make it make sense to you first. Actually read what it's telling you to do, because most probability problems tell you what to do. So when I read this, it says I need to look at just the faster refresh rate people. That is 80 people. And out of those 80 people, who do I care about? The 38 with the streaming media player. So when we do that, we get 38 divided by 80 is 0.475. Or 47.5% of the people who bought a faster refresh rate, who bought a faster refresh rate had the streaming media player with it. And this is called a conditional probability. The condition you're placing, the condition you place is the given. The condition I'm placing is that they have to have a faster refresh rate to be in the sample. Are y'all okay with that? Let's do another example. Or first, before we do another example, let's talk about what we call independent events. Because what conditionals allow us to do is they help us to establish independence. And when we talk about independence, here's what this means. If two things are independent, if events A and B are independent, then the probability of event A occurring has no effect on the probability of event B occurring. And I want you to read that and listen to me when I say it again. Read it with me. I'm going to say it again. If events A and B are independent, then the probability of event A occurring has no effect. It has no effect on the probability of event B occurring. So the question I have for you is, can events A and B occur at the same time?
Yes.
Yes, they can occur at the same time. A and B can occur at the same time. As a matter of fact, if A occurs, will that affect B occurring? Will that affect B occurring?
No.
By the definition,
No.
it says if A occurs, it has no effect on B occurring. So is the event of being right-handed independent of being left-handed for one individual? Yes or no?
No.
will my right hand, if I'm right-handed, does that have an effect of me being left-handed? Yes or no?
No,
No, 'cause
Think
you-
about that. If you're right-handed, can you be left-handed?
No.
So if I'm right-handed, does
Me-
that have an effect on me being left-handed?
some people are even-handed.
Yeah, but we're not talking about even-handed people. We're talking about right and left-handed people right now. Okay, here's another one. What about if I'm a smoker? Does that have an effect on me being a non-smoker? Yes or no?
No,
No, you can't. Yes, it does actually. Yes, yes is the answer there. Yes. If I'm a smoker, can I be a non-smoker too?
No, because you're
no, because you
Because I'm a
smoke.
smoker. So they have an effect on each other. So are those events independent?
No.
No. As a matter of fact, if one of those events occur, the other one can what? Cannot occur. What do we call
Not
that?
occur.
What do we call that?
Independent. You just
No.
said it.
It's
No.
it starts with an M, the M one.
It is the M one. What is it? The M one.
I think of it mutually.
Something.
It's called mutually exclusive events.
There we go.
The thing that I get a lot of people confused about, and the thing people get confused about a lot is that mutually exclusive and independence are the same thing. They aren't. They are totally different. Mutually exclusive means that if one event occurs, the other one cannot occur. If I'm a smoker, I can't be a non-smoker. Those are mutually exclusive. Those are mutually exclusive events. They cannot occur at the same time.
So then what-
Independence doesn't say that. Independence says that if I'm a male, and if I'm a male, I can also be a smoker. Because if I'm a male, it has no effect on me being a smoker. Does everybody understand that? Or if I'm right-handed, it has no effect on me being a Republican. Does that make sense?
Mhm.
Because those two things are independent of each other. They don't affect each other. One occurs, the other one can't occur. And the word I'm saying every time I did those two examples right there, when I said male and a smoker, right-handed and Republican, is the word and. The key word there is the word and. And when you see the word and in terms of probability, it means to multiply. So if two events are independent, then the probability of A and B is simply the product of the probability of A times the probability of B. Or another way of expressing this would be to write it like this right here. This can also be expressed as the probability, I don't know, write it way out there, right over here. And also the probability of A intersect B. Probability of intersect B. And so what ends up happening now is this. This is what we call an assumption of independence. This is what we call an assumption of independence. That's what we call an assumption of independence. Now, the problem with the assumption of independence is this. In theory, it sounds good. For instance, the fact that I'm a male should not affect the fact that I'm a smoker. Does everybody understand that? That's a pretty good theory. Or the fact that I'm a male should not affect the fact that I'm an alcoholic. Everybody got that? But in real life, what ends up happening? You start to see that a lot more men probably are smokers or alcoholics. I got that? Those two things truly aren't independent because there's other factors that affect things. All right. And so when we really want to show what we call mathematical independence, we use the conditional probability to show that. And again, this right here is the conditional probability. This is the conditional probability. That's the conditional probability. And here's what it says. If events A and B are independent, if they're independent, right, then if A given B is what I'm saying, if B occurs, given that B has already occurred, it should have no effect on A. And what that really means is that if B occurs, then all of this stuff right here, this should still be equal to just A occurring by itself. That's what this is saying. These two things should be equal to each other. Because remember what this says, A given B means what? A given B means that B has already occurred. Now that B has already occurred, now that I have all my males, what's the probability that you're wearing glasses? That should be equal to the probability that, here's what it really means, that if you wearing glasses independent of your gender, of you being male, then what should be true? The same amount of males should be equal to the same amount of males with glasses should be equal to the same amount of females with glasses. There should be no distinguishing feature between those two things, which means that they are equal to each other. And we can show this using the formula, by the way, because the formula says this: the probability of B given A is equal to, or the probability of A given B, probability of A given B is equal to, remember, we strict with the bottom, the probability of B, right? Times the probability of A and B. Well, look at this right here. The probability of A and B is equal to this term right here. Do y'all see that? The probability of A and B. And remember, where am I getting this from right here? That's just this formula I'm using right here. Probability of A and B is, probability of A given B is equal to the probability of A and B divided by the probability of B. Restriction at the bottom, intersection at the top. So here, restriction at the bottom, intersection at the top. But the intersection right here, probability of A and B is just equal to what? The probability of A times the probability of B. And all of that divided by the probability of B. What's on top and bottom? That's the same. It's probability B term. And so what this tells me now is that the probability of A given B should be equal to just the probability of A. And so what this does now is we're going to show independence, the independence of two events mathematically. This is what we call that is the mathematical formula. The mathematical formula for independence. That's the mathematical formula for independence. And in order to show it, here's what I need then. To show that two events are independent, I need a conditional probability. I need a conditional probability. And when I get a conditional probability, it has to equal what this is called a marginal probability. That's called a marginal. So the conditional probability should equal the marginal probability if two things are independent. So let's test this. Let's test this with a different example. So the following survey represents 300 households that actually purchased large TVs. The households were asked if they were satisfied with their purchases. So now here's the question. You can purchase, again, a faster rate TV, which we'll call F, and a standard rate TV, which we'll call F prime. But this time I want to ask you this question. Are you satisfied with your purchase? I don't care about the streaming media player anymore. I just want to know, are you satisfied with that purchase? So yes, you're satisfied. No, you're not. We'll say this is S again. Satisfied. S prime is no, I'm not satisfied. And so the question is this. Determine whether being satisfied with the purchase and the refresh rate of the television purchase are independent of each other. I want to determine that, does it matter? Am I more happy with a faster rate? Am I more happy with a standard rate? Am I less happy with a standard rate? Or does rate not even matter? Are they independent of my satisfaction? Now, intuitively, what do you think? Do you think the faster rate, do you think a faster rate or a standard rate is going to be, which one do you think is going to be more satisfactory? Faster or standard? Or do you think it's going to matter at all? Do y'all think it's going to matter at all before we even start this problem?
Faster rate?
You'd probably be more happy with a faster rate, right? I got that. That's what I would think too. But let's see if they're independent. It may not even matter. So here's how we test this. Here's what we're gonna do. In order to test it, we need to establish a condition first. We can set up any condition we want to. Because if one thing is independent, then they all should be independent. That's how independence works. All right, so we can set up any condition we want to. So one condition I can set up is this again. The probability of F given S. What does this say? The probability of F given S. What does that mean? Who am I interested in?
The faster standard, right?
So faster given standard, right? Faster given the what? Not standard. Given, look at it again.
The satisfied.
Satisfied
Satisfy
customers.
people. What
Yeah.
people am I interested in then? What people am I interested in this sample?
Satisfied.
I'm interested in the satisfied people. And out of those people, who am I going to look at?
The faster rate. Faster standard.
If they are truly independent, what should be true? All of those people should be equal to what people?
240.
Try it again. All those people should be equal to who? Which people?
Faster.
The faster people. All of those people, or the percentages, should be equal to each other. The way this works, if you're testing independence, and this is testing independence, is what we call this. We're testing for independence. We're testing for independence. To test for independence, you always first you're going to create a conditional. What conditional am I looking at right now? Faster rate given who? The satisfied people.
Satisfied.
That should be equal to whatever your first event is in your conditional. So it's equal to my probability of the faster people. So let's calculate this. The probability of finding a faster rate person, given that they were satisfied with their TV. Remember, this is a conditional probability. So the first thing we're going to do is we're going to set the denominator. How many people am I interested in here? What people am I interested in?
Satisfied.
The satisfied people. Here is the restriction. Here is I'm going to call it a condition. Here's the condition here, which is the restriction that I'm interested in. So I'm interested only in these satisfied people. How many people is that?
240.
240. I'm interested in those 240 people. Those represent the satisfied people. Everybody got that? And out of those satisfied people, what people am I interested in after that?
64.
The 64 that had a faster rate and were satisfied, right? So we calculate that, we get 64 divided by 240. That is 0.267. So this right here is just 0.267. If these two things are truly independent, if these two events are truly independent, then the fact that you got a faster TV should really not matter at all. Is everybody saying that? The fact that you're satisfied with a faster TV should not really matter if they're independent. It should have no effect on you purchasing a faster TV, actually. That's what this is saying. So now all I need to do is calculate the number of people who have a faster TV. How many people is that?
80.
Out of how many total people in the sample?
300.
300.
80 out of 300. That one I do not restrict. That one looks at everybody in the sample because I don't care what kind of TV you got. I care about everybody in my sample now. So we do 80 divided by 300. Look what I get. These two values are the exact same values. Does everybody see that? Because they are the same values, what does that tell me? These two events are independent. The events are independent. And look what I've done. I picked faster and satisfied. Let's pick a different one. Let's pick a different one. Let's pick standard and not satisfied. Y'all want to do that one? Let's pick standard and not satisfied and see what happens, all right? So let's calculate the probability of having a standard TV, F prime, given that you're not satisfied, S prime. F prime given S prime. What does that mean? What does F prime mean?
Your TV.
That means they had a standard TV. What does S prime mean?
Where
Not satisfied.
Not satisfied. So let's go ahead and calculate this. But this should be equal to what? If the two events are independent, what should it be equal to? What should it be equal to? The probability of what? Which one?
F
Look,
prime.
F prime. Look here. F given S was equal to just F. It's always the first event, right? F prime given S prime should be equal to just F prime, the first event. So let's calculate this now. F prime over S prime. So the first thing I'm going to do, restrict my sample. Who am I restricting the sample to? Who do I restrict the sample to?
To 240.
How many people? Look at it again.
That's not satisfied.
So how many people are not
Oh, whoa.
satisfied?
Not
Not
satisfied.
satisfied.
60.
60 people are not satisfied. So that's a 60 there. So 60 down there. And out of those 60 people, which ones do I care about?
Is standard.
I care about the ones that have a standard
44.
rate TV. How many people are those?
44.
44. So I'm getting 44 over 60 there, right? Is that equal to, what is F prime?
220.
220 out of how many people total?
300.
300.
300.
Are those two numbers equal? Calculate them. 44 divided by 60, 0.7333. 220 divided by 300, 0.7333. Do you see how I picked a totally different condition and it still told me that the events were independent? If one set of events are independent, guess what's going to happen? All sets of events are independent in a two-way table, in a contingency table. That's because if that one event is, and again, that's because what does independence mean? If this event occurs, it has no effect on the other event occurring, which means whether you get a faster or a standard rate, it has no effect on you being satisfied or not satisfied. And you've shown that mathematically through two different conditions. But when you do a conditional, when you check for independence, when you test for independence, because you're going to see things, are these two events independent? You have to establish a condition first and then set it equal to a marginal. Establish a condition first, then set it equal to a marginal. All right. So we're going to do another example. Let's do another example of this. This says, do millennials or Gen Xers feel more tense or stressed out at work? The survey below is conducted online. Use the information to answer the questions. First question. Given that the employed adult felt tense or stressed out at work, what is the probability that the employed adult was a millennial? So let's go through here and give these some letters, all right? Go through here and give these some letters. Let's go with, let's call this one M and M prime. Either a millennial or you're a Gen Xer. Stressed out at work, let's call this one W and W prime. Two variables. They felt tense or stressed out at work, yes or no? Was the first variable. Age group is the second variable. Right? Now, First one says, given that the employed adult felt tense or stressed out at work. So where am I looking at for that?
W.
I'm looking at W for that. That is W. The given here tells me to look at W. Given W. What is the probability the employed adult was a millennial? That's going to be just M. I've been doing conditionals for a long time. And every time I do a conditional, I always do it like that, by the way. I always figure out what my given is and I write it in the back first. And then I go back and set the front part. So, because this now tells me, what people am I interested in? Am I interested in everybody in the sample? Am I interested in everybody in the sample? Am I interested in all 954 people? No.
No.
I only care about who?
358.
The
stressed
358
out
people,
ones.
the 358 people that make up W, right?
Mhm.
The people who felt tense or stressed out at work. So that's 358. And out of those people, who do I care about?
The 175.
And so-
The
millennial.
175 that are millennials. Look at the next one. Is that the same thing as the next problem? Given that the employed adult is a millennial, what is the probability the person felt tense or stressed out at work? Are these two the same problems? Or are they the same things?
No.
Good. Let's look at it and see why. The next one says, this time the given is what? You have to be a
M.
M. So the
Millennial.
probability of given that you're a millennial, M. What's the probability that you feel stressed out, W, at work? Now, who am I interested in?
The 381.
Good. I'm interested only in the 381 millennials, right?
Mhm.
And out of those 381, which ones am I interested in?
175.
175.
Still the 175 that are millennials and stressed out at work. Are those going to be the exact same values?
No.
They're different values. Everybody got that?
Mhm.
And it's all because we changed our restriction. We changed who we were looking at. So the last question says this then. Is feeling tense or stressed out at work an age group independent of each other? So what I do is I'm gonna find a conditional first and then set it equal to its marginal and see if they equal each other, right? So look what I have here. I already have two conditionals already set up for me. I can pick either one I want to. I'll take the top one. I'm gonna do the probability that M given W, what should that be equal to? If they're truly independent, what should that be equal to?
PM.
The
M.
probability of M, the probability of the first term. If they're truly independent, that should be equal to the probability of M. We know that M given W already is equal to what?
175 over 358.
358. And then the probability of just M, the probability of being a millennial is what?
381.
381 out of how many?
954.
954. So all you have to do is calculate those and see if they equal each other. 175 divided by 358. 0.489. Does that equal 381 divided by 954? Do they equal each other?
No.
No. So these are not equal. That means that these are
Dependent.
dependent upon each other. Good. They're dependent upon each other. It looks like millennials tend to be more stressed out than Gen Xers, by the way. That's what this is saying when I look at the sample. Millennials tend to be a little more stressed out than Gen Xers. They have a smaller sample, smaller people, they have a smaller sample, a significantly smaller sample. Gen Xers have a larger sample with about the same amount of people, so yeah. So that's independence, and that's conditional probability. Everybody got that? Yes, y'all understand that part? Y'all okay with that so far, right? Because now I'm going to lead you into something that we use conditional probability for. And this is probably one of the most applicable parts of conditional probabilities. And it's this thing we call Bayes' theorem. Bayes' theorem is going to lead us to what we call Bayesian analysis. We're not going to work on any of that. That's too far beyond this. But Bayes' theorem has a very nice application that uses conditional probabilities. And here's what Bayes' theorem says. If the probability of A given B is equal to, look here, remember, whatever this is, that becomes a restriction. Y'all see that? So the probability of A and B over probability of B. And if the probability of B given A is equal to the probability of A and B, where did the A go? To the bottom again. We agree with both those statements, right?
Mm-hmm.
These are just conditional probabilities. So we know these conditional probabilities. And the thing about this is this. Here's how this works. Let's say that you like to go shopping. And in particular, you like to shop for expensive handbags, purses of that nature. I see you, Jeanette. That's why I said that. I feel like that'd be up your alley. So let's say you like to do those type of things, right? And you may spend your time at work on your computer shopping for, or browse. We'll call it browsing. That's what we'll call it, browsing for particular things like that. Well, sometimes when you go to your search engine and start typing things, for instance, in Google, or you go to a web page, Google starts to bring up all of these different ads of expensive handbags, like it's reading your mind. How does it do that? It's using applications of probability and Bayes' theorem to do that. It's already seen that you search for a certain thing. So it's running algorithms, and it's not this simple, but it's really running algorithms behind the scenes that says, hey, this person tends to want these type of things. Let me show them their type of things. That's what this is doing right now. So this is what this Bayes' theorem is saying. Bayes' theorem is saying that I know this piece of information already. Now that I know that, let me see if I can increase or decrease the odds of something else. And here's what Bayes' theorem here's how we can re-express Bayes' theorem. It's a very simple thing, but it says, the Bayes' theorem says the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. Let's see where this formula magically came from real quick. Look here in both these formulas. A given B, you have that term there. Do y'all see that? B given A, you have that term sitting there. Both those terms are equal. Does everybody understand that? And because they're equal, we can re-express for any one of them. In particular, I can take this entire term right here and rewrite it in terms of the probability of A and B. So I can rewrite it. Let me write that in red as a matter of fact. The probability of A and B is equal to, if I rearrange this formula for A and B up here at the top, all I have to do is multiply both sides by probability A to move it out the bottom. I'm gonna get this right here. The probability of B given A times the probability of A. So I'm able to re-express this term right here, or this term right here, using this formula right here. And why is that important? That tells me now that if I know a condition, I can find another condition. And generally what happens in terms of statistics, if you know one thing, you know one condition, you easily know the other condition as well. So this is very useful to us. And so we can replace this A and B right here with this formula right here. So literally what I've done is I've taken this formula right here and put it right here. I recalled it that, and that's how I came up with that formula there. And what you're doing is you're using, because you have this term right here, this means I know some kind of information already. Because I know that, I can do a whole lot of things with it. And one of the greatest things that we do with it involves an example like this. Here's the scenario. You have a cough and a fever. There's a chance you've caught COVID-19. you don't know what the chance is, and you don't want to take chances, so you seek advice from your doctor, right? The probability of catching COVID-19 is only 1%. So the probability you actually have the disease is 1%. For a person who tests positive, there's a 90% chance that this person actually has the disease. However, this test also produces a positive result 10% of the time for those who do not have the disease. You've tested positive for COVID-19. What is the probability of actually have the disease? So, without getting into anybody's business, if you take a COVID test, and depending on what kind of test you take, those tests have these false positive and false negative rates, right? And some of them are actually pretty high. So here's what happens. You take a test and it comes back positive. Does that really mean you have the disease? Well, if there's only a 1% chance that you have the disease to begin with, it's really rare for you to have the actual disease. I want you to understand that. It's really rare for you to actually have the disease. And this is with anything in life. Like if you look at certain rare diseases that people go to the doctor and the doctor says you have this particular cancer. What's the first thing most of those people do when a doctor tells them they have a particular type of cancer? They go get a second opinion. And that second opinion is done because of the rarity of the disease and also the false positive and false negative rates of the disease. So when we do this, what we're going to do is we're going to look at this question. Here's the question we're trying to answer. I want to know, you've just tested positive, right? I got a positive test. How many different ways can I get a positive test is my first question. Do I have to have the disease to get a positive test? No. I can get a positive test even if I have what? If I have no disease, I can get it, right? That's called a what? No disease and a positive test is called a false positive, right? Likewise, I can get a negative test and still have the disease. That's called a false negative. In general, which one's worse? False positive or false negative here?
False negative.
False negative. Why is a false negative worse?
Because then you think you don't have it.
You're walking around with a disease that you think you don't have. And you're potentially not only maybe killing yourself, but you're also spreading it to others, right? So let's keep that in mind here. This is a real life scenario. So here's how we do this. And this is where we're gonna use a decision tree. In most Bayes theorem problems like this, you can always tell a Bayes theorem problem. You start to get a whole bunch of probabilities popping up within the problem first off. So you're gonna create branches. Your first branch, or your first job is actually to determine your events. There are two events here, all right? And the event is either you have the disease, the event is disease, which is made up of either you have the disease or you don't. And the other event is the status of your test, which is either positive or negative. All right. So when I start this, I need to look at myself. You could try both ways, but you need to start on the branch that is going to be the one that only has two options. In this case, that would be you have the disease or you don't have the disease. And then from there, you're going to branch out with positive, negative for if you have the disease, positive, negative if you don't have the disease. So when we started, here's what I'm going to do. D prime. What does D stand for?
Disease.
What does D prime stand for?
Just
No.
don't have the disease.
What percentage of people have the disease?
90.
90%.
What percentage of people have the disease?
Oh,
1%.
1% of people have the disease. So on this first branch, that's 1% of people. If 1% of people have the disease, what percentage don't have the disease?
99.
99.
Only 99.
So this is what we call our complement. We're using the complement now. If 1% has the disease, the other 99% of people don't have the disease. They have to add to 100, right?
Yes.
Next thing. Now, if you have the disease and you take a test, you can either test positive or negative.
Negative.
If you have the disease and you test, if you have the disease, what's the probability you test positive?
90%.
90%. Which means what percentage of people won't test positive and have the disease? 10%. If you don't have the disease, you can also do what? Test positive,
positive.
or negative.
Hmm.
What percentage of the people test positive that don't have the disease?
10.
10%.
10%.
What percentage of the people test negative that don't have the disease?
90.
90.
There you go. Now that we have this tree made, right? Here's my question, and here's the conditional part of the question. You have tested what already? You've tested positive. What is the probability you actually have the disease? If I set up a condition for this, what is the condition going to be? You have tested positive. So given what? Given that you are positive, what's the probability that you have the disease? That's how we set this conditional up. Does everybody understand how I got there?
Okay.
Because I need this part to make sense for you right now. Because this is what we've been talking about. This isn't a new part yet. Really, none of it's new. It's just the tree we created. The tree got us here. We've created the tree. Now we're looking at this. You have tested positive for COVID. That means that is the given. Did I say the explicit word given there? No, I didn't say that was explicitly given. But we know this is given. You're testing positive. You've tested positive. Now that I know this piece of information, you tested positive, what is the probability you actually have the disease? So who am I interested in?
90%.
I'm interested in which branches? Let me ask those branches. Let's
The
say
top.
branch. So I'm interested in this branch right here because they did what?
Positive.
They tested positive. I'm also interested in what branch? This branch right here because they also did what?
Positive.
Tested positive. And the assumption now, here's what we're going to make. Here's the assumption we're making. We're making the assumption that these events are independent of each other. They're independent of each other, although they're really not. If you have the disease, you should test positive. That's what we want to happen, right? And if you don't have the disease, we want you to test negative. By the way, this branch right here, when you test positive and you have the disease, this is called sensitivity. That's the sensitivity of a test. This branch right here, when you don't have the disease and you test negative, that's called the specificity of a test. So there's sensitivity along this branch, specificity along this branch. You want these to be near 100%. That is a great test. You want a test that will always tell, if you have the disease, you want a test to tell you that you're always going to be positive for it. You also want a test, if you don't have the disease, it's always going to tell you that you don't have the disease. You want to maximize these values out here on the outsides, and you want to minimize these values on the inside. Because these are your error rates. This one is a false negative. This one is a false positive. So to calculate this though, because we're independent of each other, all you have to do is this. To find the probability of having the disease and testing positive, you just multiply those things on that branch. So you would multiply 0.01 times 0.99, and I get 0.099.
Is it 0.99 or 0.9?
It is 0.9. Thank you so much. 0.01 times 0.9, 0.009. Same thing along this branch. Multiply 0.01 times 0.10. I get this right here. I want you to realize this too. If I add up these two values, what do I get? What's 0.009 plus 0.001?
0.101.
That is 1%. What does that 1% represent? All the people who have what? The disease. Right?
Okay.
This is all the people who have the disease. These numbers right here are your marginal totals, by the way. They're going to add up to your marginals. This number is a marginal. This number is a marginal. This represents all people with the disease. This represents all the people without the disease. On the next branch, 0.99 times 0.1. .099. 0.99 times 0.9, 0.891. Again, if you add up 0.891 plus 0.099, look what you get, 99%. So when I look at this tape, when I look at these branches already, it already tells me what? If you look down here at this branch, most people are going to what? Test negative and not have the disease. As a matter of fact, if you look at this branch right here also, most people are going to just test, are not going to have the disease, period. Which we would expect because the disease rate is only 1%. So we should be getting a whole lot of people without the disease in the sample to begin with. And the ones that don't have the disease, they should test about 90% of the time negative for the disease. But here's what I'm interested in now. Remember in a conditional, what do we do in a condition? We restrict it to what are we interested in? Which people am I interested in?
Positive.
I'm interested in all my positive people. Where are my positive branches at?
The first and third.
0.009 and 0.099. Does everybody see that?
You add them up together?
Yes, we do. And that is the
Okay.
bottom of the denominator. So we're going to add up
0.108.
0.009 plus 0.099. That is all the people who have tested positive for this particular disease. Now, out of both those sets of people, which one am I actually interested in?
0.01.
Try it again. You're close. Who am I interested in? These people have tested positive and don't have the disease. These people have tested positive and they do have
Would
the
it be
disease.
0.009?
I am
okay.
interested in the 0.009 people, yes. The 0.009 people. Why I'm interested in those people? These people have what? Have the disease and they tested positive. These people are all of the positive people. So when I calculate this, here's what I get. 0.009 divided by 0.009 plus 0.099. The probability that you have the disease, given that you tested positive, is only equal to what?
0.083.
There's an 8% chance that you actually have this disease, even though you tested positive. Which is a really small chance, by the way. Why is it a really small chance?
Because it's only 1%.
Only 1% of the population actually has the disease. On top of that, your false positive rate is so high to begin with. Your false positive rate is 10%. So intuitively, this doesn't make a lot of sense until you start to break it down. Because if only 1% of the population has the disease and there's already a high false positive rate, chances are the test that I got back was a false positive test. Or at least I'm praying that it's a false positive test. But this is what we call Bayes theorem, and it's how you use it in real life. So, one more. I think I got one more. Yeah, let's try this one. Try this last one. A test for a disease gives a correct positive result with a probability of 95% when the disease is present, but gives an incorrect positive result, a false positive, with a probability of 0.15 when the disease is not present. If 5% of the population has a disease and Gene tests positive to the test, what's the probability that Gene really has a disease? 2 branches. And these branches, typically the problems you're going to do are always going to be like disease type problems like this. You can do other things like this. We generally do disease. But your first branch is whether they have the disease or they don't have the disease. D and D prime. Probability a person has the disease is what?
95.
Get it again. Has the disease.
0.95.
Oh,
Try it again.
5%.
5%.
If 5%
Has
of the
the
population has the disease, you got to read that. If 5% of the population has the disease, what percent of the population doesn't have the disease?
95.
95% of the population does not have the disease.
0.1. Oh, it says not present. I see.
Right. So let's look at the next part then. Either you're going to test, when you test, you can test how? You can either test positive or you can test negative. on each branch. A test for disease gives a correct positive result with a probability of 0.95. So where does that belong? What branch is that going to be on?
On top.
On
On
top,
the
which
top
is
one.
DN plus, right?
Yeah.
Yep.
0.95. So what is the negative result going to be there?
0.05.
0.05. But it also gives an incorrect positive result. Where is that going to occur at?
In the
D
bottom.
prime and positive, which is
Positive.
going to be 0.15, which means it's correct how often?
0.85.
0.85. So gene tests positive to the test, which means that given that you're positive, what is the probability you have the disease, right? So the probability of, given that you tested positive, what's the probability you actually have the disease? You okay with that?
Mhm.
Who am I interested in? I'm interested in which people? What's the denominator that's going to be?
Positive.
Just the positive people. I only care about positive people in the sample. Remember, I look at here to restrict.
Mhm.
So I only care about this branch and that branch. So on that top branch, 0.05 times 0.95, 0.0475. We can finish calculating all branches, by the way. I like to calculate all branches just to be on the safe side. This should also be 0.05 times 0.05, 0.0025. Add those up, you're going to get 5%, right? 0.95 times 0.15, 0.1425. 0.95 times 0.85, 0.8075. And now all we have to do is this, remember, restrict our denominator. Who's in the denominator? What people I'm looking at in the denominator?
0.1425 plus
Good.
0.0475.
So this is 0.0475 plus 0.1425. My positive branch people, right? Go down there. Who goes on top?
0.0475.
The people that are positive and have the disease. People that are positive, that tested positive and actually have the disease. Calculating that. I get the 25% chance that you actually have this disease. 25% chance you actually have the disease. So this is an application of the conditional probability that extends into what we call Bayesian analysis. This is what we call Bayes' theorem. Are there any questions on this particular thing right here?
No.
Hey, I want y'all to make sure y'all practice this. Practice it, try to practice before the weekend, because if you don't, you're gonna forget it. And it seems complicated, but it's really not. It seems very complicated, but it's really not. It's really, once you make this tree, once you have the tree made, everything else flows from the tree. It's just finding the correct branches. And most time your branches are gonna be positive. That's what you're interested in. And again, these are, you can apply to different things. If you start to see a whole bunch of probabilities, try to do a tree. You could have did this with a table too, by the way. You can convert this tree to a table, right? Where your table, this would be the inside cells. All of these are your inside cells. Yeah, real quick before I go. So things are, you have disease prime. You have a positive test and a negative test. And you have total and you have another total out here. So I can convert this to a tree just by doing this. First branch, disease and positive, goes in this cell right here. You see that?
Mm-hmm.
So that is equal to 0.0475. Disease and negative goes in this branch right here. That is 0.0025. That is 0.0025. If you add these up across, what do you get? 0.05, and that's all the people that have the disease. See how they worked across the branch? Other one. The no disease and positive would be 0.1425. No disease and negative would be 0.8075. Add those up.
0.95.
Now, if you add down right here, 0.0475 plus 0.1425, you get the positive rate, which is 19% of your tests are going to come out positive, right? If you added the other ones, 0.0025 plus 0.8075, the other 81% are going to come out negative. And that's the information that wasn't given to you in the problem, by the way. That information wasn't given, so you can find it by creating this table. When you create the table, you can get the positive rates and the negative rate. This 19%, by the way, is what you're putting down here. So 19% of the total tests that were given tested positive. 19% of all tests given tested positive. The only ones I'm interested in are the ones that had the disease and tested positive, though, which is that which is that percent right there. So what that really means is that 75% of the tests that test positive are really false negatives. It's crazy. It's a lot. Anyway, so if y'all have any other questions, I'm done for the night. Y'all have a good night. Remember, the test, I put the retest on my math lab. So you have until Friday to get that done. And if you make less than an 80, you can take it. Anything better than 80, don't worry about it. Also, if you didn't turn a project in, it's late, but you can turn it up 10 points off. Y'all have a good weekend. I will see y'all on Tuesday next week.
Thank you.
Okay.
See you,
have a good
Professor.
weekend too.